Okay. Okay. Thank you. Thank you, sir. Thank you, sir. Okay. Good evening, everyone. Thank you for inviting me. So today my topic is perfect powers in recurrent sequence. Sorry for because I didn't get much time. So I'll try my best. Okay. So before going to perfect power, you should know what is actually perfect power. So many problems in number theory may be reduced to finding an intersection between two sequences. Like it may be perfect power, it may be anything. So normally we're finding in case of number theory, generally we're finding the intersection of two sequences. So it is depending on the what are the type of sequence you are following. Like if you have a sequence like it is growing exponentially, so it may possibly we may not get much intersection between the two sequences. So if the sequence is growing very slow, so it have a possibility that you will get a much more intersection between the two sequences. So in several situations, such statement may be made for precise. Like for example, we'll think like if you pick any two sequences to be a non-generic binary linear recurrent sequences. Okay. After that, I'll discuss what is the binary linear recurrent sequences. So if it depending on the two sequence, if I'll follow one binary linear recurrent sequence and one of the sequence is the sequence of perfect power. So you have to find the intersection between two. That is actually a problem of perfect power in finding in linear recurrence sequence. So the problem of finding all perfect power in the Fibonacci sequence, I think you already know what is the Fibonacci sequence because in nature we are already, so you can see in everywhere, we will use the Fibonacci sequence. Like Fibonacci sequence is nothing. If you add the previous two number, we'll get a next number that is called Fibonacci sequence. If you go for the application also, we'll get in the micro how it multiplies. It may be in flower also. If you take the petal of a flower, that is also will get a Fibonacci sequence there also. So Fibonacci sequence you can see in the nature always. Before that, I go what is perfect power. Yes. So perfect power is a natural number that is a product of equal natural numbers. It may be 2 square, 3 square, like we know already. So it is something like an integer that can be expressed in the form of m to the power k. So that number is called the perfect power. For example, we'll take k is equal to 2 or k is equal to 3. It's called as perfect square or perfect cube. So in general, trivially you can see 0. If you pick any k, 0 as a trivial perfect power, and if you pick k for any k, 1 is a perfect power always. So there is a two trivial perfect powers in the total whole number. A sequence of perfect power can be generated by iterating through the possible values for m and k. In 2002, a mathematician proved that an unsolved problem that the only pair of conjugative perfect square is 2 to the power 3, that is 8, and 3 square, that is 9. Only perfect power which has a difference of 1, that is 8 and 9. So only perfect power we have 2 to the power 3 and 3 to the power 2, and that is a Catalan conjecture. Later, the Pillai proved the conjecture that for any given k, for any given integer k, there are only a finite number of pairs of perfect power whose difference is k. There it comes why I'm telling the difference between two perfect power. There it comes, the problem is called the equations. We're finding the little special type of equation for which we're finding the solutions, but we're finding only the natural number solution, only finding the integer solution, what I'm telling. So there it comes, the Diophantine equation, and any polynomial equation with one or more unknowns such that only integer solutions are studied, then it is called a Diophantine equation, because we are only considering about the integer solution, not the rational or irrational solutions. So that equations are called the Diophantine equation. In the year 1900, the Hilbert presented a list of 23 famous problems, out of which the 10th problem is about the Diophantine equation. The problem concerned that if you can provide any general algorithm to solve any Diophantine equation, is there any general algorithm exist or not? There one mathematician proved, the mathematicians proved that there is no such algorithm exists. We have to check the Diophantine equation, and for each type of Diophantine equation, we'll get a different type of methods we can see. So there is no such exact algorithm for that. So there give rise to many interesting methods to solve these equations, such as use of congruence model, power of p, that the elementary way can follow, and factorization over the number field. It may be number field of integer or Zn, integers model p or model n. We can follow any number field and factorize it so that we can find a solution for the Diophantine equation. One more method is using the modular form, and one more method is to form a Pell's equation from the Diophantine equation. So that the Pell's equation is very popular because we already know the solutions, how the solutions of a Pell's equation look like. So it is easy to convert any Diophantine equation to Pell's equation so that you can get a solution from there. And one more famous, nowadays we are already using the elliptic curves. So we can find the solution of a Diophantine equation. These are the methods, since there is no exact algorithm for Diophantine equation. So in the famous examples we can see. The next one, I have a Pythagorean triple. We already know in the in primary also we already know, if you have a right angle triangle, the perpendicular square plus base square is equal to the hypotenuse square. There we'll get a Diophantine equation, that is x square plus y square is equal to z square. We already know how the equations or how the solutions look like. There by this generalizing the Pythagorean triple, the former last theorem exists, which is that the Diophantine equation x to the power n plus y to the power n is equal to z to the power n, for n is more than 2. So it has a solution or not. Recently, the Willy proved that it has no solution for any non-zero integer x, y, z when n is an integer which is n greater than 3 or equal to 3. So if n, the only possibility is n is equal to 2, we'll have a solution. For more than 2, we can't have a solution for the former's last theorem. And one more interesting property from the Pell's equation, because I have already discussed in the previous, right? We can't have any perfect squares or perfect powers which with a difference of +1 or -1, with a difference of 1. So there it comes, one more equation that is called Pell's equation. If you change, if you add one d there, like x square minus dy square is equal to plus or minus 1. There is a little bit generalization for that one. So it has a solution or not. So we'll always have a solution and has a specific type of solution from that. So it is proved by the Pell. So it's called the Pell's equation. So if x square minus dy square is equal to plus or minus 1, it has a solution. Then it look like xn plus yn root over of d is equal to a plus b root d to the power n. It look like something like this, and a plus b root d is the minimal element or fundamental solution of the Pell's equation. And I'll give some more properties, like we have one Pillai's conjecture. Same thing, if you can have, like I have already told you, right? Only 9 and 8 are the perfect powers which has conjugative or which have a difference of 1. To generalize that one, Pillai's conjecture that if can you have a perfect power with a difference of k or not. So there the Pillai already proved that for any integer k, the Diophantine equation a to the power x, any perfect power minus b to the power y is equal to k, has only a finitely many positive integer solution. We can't have infinitely many. We may get a finite number of a positive integer solution for these type of equation, and there is only one value of k for which the Pillai's conjecture is solved, that is called k is equal to 1. That's why I'm telling the only conjugative perfect power exists, that is 9 and 8. We can't, there is no exact solution for other case. So there are only finitely many pairs of conjugative integers which are perfect power. That's what the Pillai proved that. And then Tiedemann also proved in 1976. Next we have Catalan equation, one more example for the Diophantine equation. So there it comes. If you have x to the power p minus y to the power q is equal to 1, it has only one solution, that is 3. That is okay. X is equal to 2, x is equal to 3, and t the prime is 2, and sorry, x is equal to 3 and y is equal to 2, and the only primes possible is 2 and 3. There only the only possible solution for this. There's the only one solution, that is 3, 2, 2, 3. And one more Bill's given one more equation from there, just to generalize that one of the format last theorem, because in the format last theorem we have seen we have taken powers as the same, right, n and n. But to generalize that, the Bill's given one more equation to take by taking different you can say different powers. Like in the first term we have taken p as the power, q as the second power, r as a third power. It has a solution or not. He is given one more condition, that if 1 by p plus 1 by q plus 1 by r must be less than a 1, then only we can find exactly 10 solution for that. I given 10 solution here, like 1 plus 2q is equal to 3 square, 2 to the power 5 plus 7 square is equal to 3, 4. You have 10, exactly 10 solution for this problem. So if you have a Pell's equation, it's look like something like this. With little bit generalization of the Pell's equation, they have given one negative Pell's equation. Negative Pell's equation means what is the solution of the Diophantine equation? X square minus dy square is equal to -1. They have also generalized that too by taking the right side as k, and they have proved and have given some exact solution how it look like. It look like something like this. If you have a solution for xn and yn, so xn plus yn root over of d is equal to a plus b root d to the power n. That is the fundamental solution of that equation into x plus y root d. It look like something like this. That is the exact solution of the Pell's equation. Okay. So why I'm telling recurrence sequence? So recurrence sequence is nothing like if you have a set of terms. So if you can find the nth term by using the previous terms, so that we can find a recurrence sequence. So that is a definition of recurrence sequence. If you can find the nth term by using the previous 2 or more or any n number of terms also, so that is called recurrence sequence. One recurrence sequence, I have given one example like Fibonacci sequence. That is also one recurrence sequence. So this is a general form of recurrence sequence. Something like this: an is equal to some constant into an minus 1 plus some constant into an minus 2 up to g to the power n. So you can find the value of n by using the previous n minus k terms, or exactly k terms. So yeah. But there are some interesting property of recurrence relation, we can say. By using the recurrence relation also we can find the how the terms look like by finding the roots of the characteristic equation. How to find the characteristic equation? For example, I'll pick a n as some r to the power n. I don't know what is r. R is any constant. So if you pick a n, any term in the form of r to the power n, so by using in the recurrence relation, we can easily find what is r and how the nth term look like something like this. An is equal to alpha 1 plus r1 to the power n plus alpha 2 into r2 to the power n. Something look like this. I'll give one example that will be better for you. So if you pick any Lucas sequence, okay, why I'm telling Lucas sequence, that is a specific sequence of for the binary recurrence sequence. If you pick the initial term as u0 as 0 and u1 as 1, that is called Lucas sequence. It look like the binary recurrence. Binary means you have to use only exactly two term of the previous two term, then we can find the nth term. So it is something like u1 is equal to some constant into un minus 1 plus some constant into un minus 2 with initial term as 0 and 1. So that is called Lucas sequence. So we can easily find how the terms look like by using this binary recurrence. So these forms are actually called binary forms of un. And there is one more sequence that is called associated to Lucas sequence. The associated Lucas sequence is same as the same binary recurrence, but the difference is it starts with 2 and a, and the binary form look like this: alpha 1 to the power n plus alpha 2 to the power n. I give some example, like I have given Fibonacci sequence as one example, right? So if you see, if I pick a as 1 and b as 1, it is something like the sum of the previous two term is equal to the next term, right? So it is something like Fibonacci sequence. So if I pick a as b as 1, so it is the Fibonacci sequence, and the Binet form same as this one, but alpha 1 alpha 2 will be 1 plus root 5 by 2, and alpha 2 will be 1 minus root 5 by 2. Then it comes one more sequence that is called balancing sequence, which is given by the Professor G.K. Panda. So I'll give what is the balancing sequence now. But if you pick a is equal to 6 and b is equal to -1, then we'll get a one more Lucas sequence, but different alpha 1 and alpha 2. There alpha 1 will be 3 plus 2 root 2, and alpha 2 will be 3 minus 2 root 2. And one more will be Pell and Pell Lucas sequence. That is also very familiar. If you go for the continued fraction, you get the numerators as the all Pell sequences, and the numerator will always be Pell Lucas sequence. So that is also will get one more sequence there, binary sequence. The binary sequence is if you pick a is equal to 2 and b is equal to 1, we'll get a binary sequence for the Pn and Rn with different alpha 1 and alpha 2. There alpha 1 is 1 plus root 2 and alpha 2 is 1 minus root 2. So I'll give what is the actual balancing sequence. That is my guide given, or that is the, like, think like if you have a number, if you add all the numbers from 1 to some extent like b minus 1, and I just pick one more, that b plus 1 to b plus r. If I'll add both left side and right side, I'll get a same number. That is actually balancing the left side and right side. That's why he is given the name as balancing sequence. So balancing sequence is the solution of all the solution of the Diophantine equation 1 plus 2 plus up to b minus 1 is equal to b plus 1 to b plus r. If you add the left side and right side, we'll get a specific number that is called balancing number, and the r is called the balancer of that balancing number. So it also satisfies one more binary sequence. That's why I've given here. If a is equal to 6 and b is equal to 1, b is equal to -1, I get a binary recurrence sequence. And one more interesting property is if you pick any n, 8bn square plus 1 is always a square. So if you pick any n, 8 into some balancing number square, plus 1 is always a square, and that specific number is nothing but Lucas balancing number, that is Cn, which satisfy the same binary recurrence as the balancing sequence with different initials. That initials is 1 and 3 with same binary sequence as 6bn minus bn minus 1, but different initials as 1 and 3. And it also related to the famous Pell and Pell Lucas number also. Why? The half of the Pell Lucas number is nothing but the associated Pell number, and the balancing and Lucas balancing number are connected to the Pell and associated Pell numbers. Why I'm telling? Because if you can see this, the Pell sequence, actually even terms of the Pell sequence is nothing but twice of the balancing sequences. And if you multiply the Pell and Pell Lucas, then we'll get a balancing number there. And one more property is, if you check all the even terms of the associated Pell numbers, will get actually a Lucas balancing number. That's why both are interrelated to that, because you already know Pell and Pell Lucas sequence and Pell and properties of Pell and Pell Lucas sequence. So it is easy to find some properties of BN and CN also. Okay, so we have so yes, Sudhanshu Sekhar Rao, Dr. Sudhanshu Sekhar Rao, and Professor G.K. Panda have also generalized that balancing sequence uh, to replace by replacing 6 with any A actually, because we can see if I pick A as 2, actually 2xn minus 1 minus xn minus 2, and actually I'm getting a natural numbers. I'm getting all the natural numbers. So that's why we're not considering A is equal to 2. If you check A more than 2, we'll get a different type of sequence. That sequences is called the balancing like sequence, with initials as 0 and 1, and by satisfying the balancing, the binary vectors too. And it is also have some similar property with balancing sequence, because if you pick like number square plus 4, will get always a perfect square. That's why it is related to perfect square. Why I'm telling the perfect square in recurrence sequence, because actually we are getting a if you add something, if you delete something, then we'll get actually perfect square. So that number, the square root of this number actually is the balancing associated balancing number, which also satisfy the same binary recurrence sequence, but with we can say different initials. The initials is 2 and A. It also has a binary form as alpha 1 with A plus root over of A square minus 4 divided by 2, and alpha 2 is A minus root over of A square minus 4. If you have a balancing like sequence, they have also have generalized to Pell like and associated Pell like also, which is has same type of relation with balancing like sequence. So we have generalized this one. What is my actual, I'm discussing what is my contribution in finding the perfect square in balancing in any recurrence sequence. So we'll discuss that. Before that, we have to find what are the perfect power we already got in the famous sequence, like you can say Fibonacci sequence also. So problem of finding all perfect square in Fibonacci sequence was a famous open problem for over 40 years and has been resolved only recently. That the Finkelstein found all perfect square in Fibonacci and Lucas sequence. You can say 0 is the trivial one actually. And if you pick F1 and F2, that is actually 1. 1 is also, we already know, that is a trivial perfect power. And if you pick F12, that is 144. And 144 is the square of actual 12, right? The 12 square is for 144. So these are the numbers. The Finkelstein already found that the only perfect square remain in the Fibonacci and Lucas sequence. Then the Bouguered and Siksha already generalized that by finding the perfect powers among the Fibonacci numbers. There he found that 0 and 1 and 8 and 144. And in case of Lucas number, the only perfect power exists, that is 1 and 4. Next, little bit more generalization. The Pethwan in 1992 and Sora and Stewart in 1987. Yeah, they have found that the only finitely many perfect powers exist any binary recurrence sequence. So because there is no formula that you have to find, because the sequences are actually growing very faster or exponentially, so it's not easy to find always. So they have given one more proof that we can find only finitely many perfect power exist in any binary recurrence sequence with discriminant will be A square minus 4b must be greater than 0. Then we can find a finitely many perfect powers. Then little bit particular about that, then we have found about the Pell sequence actually. So the only solution of the Diophantine equation Pn is equal to y per n, that is actually perfect power in Pell sequence. They have only found two solution. That is, one is, you can say P7 is 13 square, and the trivial one P1. P1 is nothing like 1. So that is the trivial one. They have found one more non-trivial, that is P7, the seventh term of the Pell sequence, the only non-trivial part. that is called 169, that is 13 square. So they have found only 2 solutions for the Pell sequence. They have also tried to find for the associated Pell. So you get only one trivial solution, that is 1 and 1. And then Day and Routh in 2017 proved the only perfect power in Lucas balancing, that is C0 is equal to 1, and the only perfect power in the balancing sequence, that is B1 is equal to 1. There is no other perfect power exist in balancing sequence or any Lucas balancing sequence. So they have already proved in 2017. So after that, we have tried to find, me and my guide have tried to find, is there any possible that we may get an perfect square little bit less than 1 or more than 1. So that is our problem. So the first few terms of Bn we already got, because initial is 0 and 1. Next 6, 35, 204, 1189, all are the balancing sequences, balancing numbers. And the few terms of balancing like sequences look like 0, 1, a square minus 1, a cube minus 2a, and so on. So we have already, Day and Routh already proved in 2017 that the only balancing number which is a perfect square exists, that is B1 is equal to 1. So you can see that if you add B3 is 35, right? If you add in case of 35, 35 plus 1 is actually 36. We already know 36 is a 6 square, right? So you are getting one non-trivial solution for this, which is at most perfect power, not exactly perfect power. So B3 is one, almost perfect power. We can see X3 also. X3 is a square minus 1. If you add, in case of a square minus 1, if you add one more 1, that is actually a square. So if you have any a, X3 plus 1 is always a perfect square. And for B3 also, B3 is already a almost perfect square. So same property, if I delete 1 from there, like B1 minus 1 and X1 minus 1, that is actually 0. 0 is already know that is a trivial power. So we are getting some non-trivial solution for the almost perfect power or almost perfect square. So these are we are getting by observing. But we are trying to prove, is there any other solution exist with these properties? This type of problem already tried by Bougade also for Fibonacci sequence. So they have found all the integer solution of Fibonacci sequence. Any Fibonacci number plus 1 or minus 1, that is the almost perfect power, assuming by using the factorization of fn plus or minus 1. So they have found some solution from there. And Alexei and Tangley also try to find by some generalization by taking any Lucas sequence with ax square plus b. Is there any solution exist or not? So we have found only finite number of solution exist. We can't have infinitely many solutions. So here we find that all the elements of the form any perfect power plus or minus 1 in the balancing sequence. We also generalized the same problem by taking all the balancing like sequence in the form of y square plus or minus 1. So particularly, we have found that only balancing number that is 1 less than perfect power is B3, and the only balancing number which is 1 more than perfect power is only B1. In the same case, we have a balancing sequence also. There is only one term X3, which is 1 less than perfect square, and no term in more than a perfect square. We have tried same thing. We have also tried to find some factorization so that will be easy for you to get the solution. So we have tried to find some factorization for Bn plus 1 and Bn minus 1. We have found the factorization we have found. Same thing in case of M balancing sequence also, balancing like sequence also, xn plus 1 and xn minus 1. We have tried to find the factorization for this. And by using the factorization, we have tried to find some solution because we already know properties of Pell sequence and Pell Lucas sequence, and have some property of balancing and balancing Lucas sequence. So by using that also, and by using this factorization, we try to find the solution of this. So okay, so we're getting only one. So if n is any natural number and p is any prime, so then only possible values in the balancing sequence, which is in the form of yp plus 1, that is only for n is equal to 1. And if you have any balancing sequence which is in the form of y to the power p minus 1, So that is only possibility is n is equal to 3. There is no other term exists. So I have proved this. Same for only possible values in balancing like sequence, which is in the form of w square minus 1. That is for only n is equal to 3. And in case for w square plus 1, we don't have any solution for this. So we have proved this one. We have taken only one more generalization from there. So think like we already know that b3 plus 1 is a number. Is there exist any solution that if you add any two term of the any sequence, can you find one perfect square or perfect power or not? Like you can see, if you add b3 and b1, I'm getting a 6 square, right? So that is actually 36. So if you add, if you differentiate between b4 and b3 also, you're getting a 13 square. So we're getting a non-trivial solution from there. That is by observation from. So is there any other pair of balancing sequence or any other pair of balancing number or balancing like numbers exist with these same similar property? So I have tried to prove that by forming one Diophantine equation and try to solve it. So this type of problem also like done by Patel also by taking Fibonacci numbers. So they proved that the Diophantine equation Fn plus or minus Fm is equal to y by p, and they have found some solution, some non-trivial solution from there. So we have just generalized by using the balancing sequence. So we have found exactly, we have found some solution from that. Like you can see, if you add two balancing number, the only possible n and m will be, it may be 1 0 or 0 1. If you take 3 1 or 1 3, so that is the only possible solution for bn plus bm. And if you pick the difference between two balancing number, that is a perfect power. The only possibility will be n and m is equal to 1 or 0 or 4 and 3. There is the only two solutions exist. So same for the balancing like sequence also we have tried. So we are getting not exact solution, we are getting like if you pick if xn plus or minus xm is equal to y square, the only possibility is if n plus m is equal to these numbers or minus m is equal to these numbers, generally we can find the exact solution for this. Or same thing, if you have n plus m or n minus 1 is a 1 or 3, that is only for the, if you have n and m are different parity. Different parity means one is even, one is odd. That is called opposite parity. And if you have a same parity means both are even or both are odd. So there, the only possible n plus m or n minus m will be 0 to 4, 8, 16. Okay. There also we have tried to find some factorization for that. And by using these factorization, we have proved that statement. Yes. So we got this. So these are some reference I have used. And the first paper, like balancing and balancing like numbers, which are one away from perfect power, that is published in Bulletin of Brazilian Mathematical Society. That is already published in 2019. And the recent paper, that is perfect power in sum or difference of two balancing or balancing like sequence, that is already submitted. That is on the revision, by the way. So it's not published yet. Thank you. Is there any question? Yes, sir.
I have one question. Okay. Sai, sir, you first question. uh, is there any general method to solve this kind of perfect powers or perfect squares like this?
For any sequence.
Means other than using this factorization method,
Okay.
is there any other method to solve this kind of or to handle this kind of Diophantine equation?
For specific, yes, we can say, but we can find not exact solution. But yes, we can say that you have a finite solution or you have an infinite solution. That we can say, but you can't find the exact solution for if you don't have the factorization.
I mean using either some elliptic curve or certain kind of algorithm.
Yeah, that that will be used for finding if you have a finite solution or not. Like if you don't have any solution or finite solution, that we can say by using the elliptic curve, also by using the linear algorithm.
But
We can
obtaining
easily
the but obtaining
exact
exactly
solution.
all
We
the
can't
solution
find
is
exact solution.
not
Yes.
quite easy.
No. If you pick exact man specific sequence, yes, we can you can do, I think. But if you take the generalized, like balances like sequence is a generalized one. Like if you change A, then Akasanka, yes.
Yes, yes. So I have a very small doubt. Like you have mentioned about the balancing like sequence and the
Okay.
recursive definition of that, where you used some constant A,
Okay.
capital A.
Yes,
So
yes.
my question is there any bound to that constant A? Means you took
Yes.
like A
Mm.
equal to 2, 3, 4. So is there any bound to that constant, or you can take any constant?
Minimum is more than two. Maximum you can
Yes.
take. Minimum is why I'm telling two, because if you check two, right? If you pick two, that actually I'm getting a natural number. So there is no point to study the natural number because you already know all the things. So better to go for the higher numbers. So going for the higher numbers only.
So is there any upper bound for that?
No, because the balancing like sequence is growing very fast, like exponentially. If you go for B10 or B11, then you get a bigger number, like 10 bits or 11-bit number. So it's not easy to, I mean, study. If you pick, like you can pick bigger number, so it will get a bigger. I mean, you can say 50-bit or 70-bit also will get. So that will be
Okay.
not easy to study.
Okay.
You
Okay.
have to go
Understood.
for the supercomputer.
Okay. Thank you.
Thank you. Is there any other question? Anyone? Any real life application for balancing number? Okay. Any real life application? So, ma'am, you can see in a cryptography we are already using, like in case of you are already using prime numbers and all the thing. If you're getting a complicated sequence, that will be easy in the cryptography, so that we can, I mean, it's not easy to, you'll get a more security, right? So we have to find a tricky sequence we can see. There also we can use, I mean, yes. I mean, I don't think one more app is in there, but mostly cryptography you can use.
And as far as I know, recently one or two papers are only
Easy to
there
tackle
regarding
when you
the
go
application
for
of
these.
balancing number that has been used in the finite state machine. So
Yes,
one or two paper by Professor P.K. Ray, there are one or two papers where the application of balancing number has been discussed in the finite state machine and in cryptography. There is a small application what he has discussed in his paper. Actually, Fibonacci numbers are since means ancient years. You can say they are very old. But now in real life application or in computer security system, now Fibonacci numbers
yes.
are being used or coming into application. So the other recurrence sequences, hopefully in next some years it may come.
Yes, sir. Thank you, sir. Right? Okay. Yes. Thank you, sir. It's my pleasure. Okay, sir. Okay, sir.